Welcome to ECE 3300 at the University of Utah. Today in lecture number 13, we're going to study impedance matching. The things that we're going to learn are how to add parallel and series lumped elements to a circuit, and then how to design single stub matching networks with either series or parallel stubs that are open or short-circuited on the end, and we'll also talk about matching systems with a quarter wave transformer. The idea of doing a stub match is suppose that you have a load like this, ZL. And let's suppose that it's mismatched from the transmission line, which has a characteristic impedance of Z0. If we wanted to be able to match these, one of the things that we could do is add a series stub. The series stub would have a length L, and it would be a distance D from the load, and would be either open-circuited or short-circuited. If we wanted to add a parallel stub instead for our load ZL and characteristic impedance Z0, we could simply put a stub in parallel where the distance D, telling us how far it is from the load, and the length L of the stub are defined again, and it could be either open-circuited or short-circuited on the end. So if we want to design a single stub matching network, what that means is that we're going to be defining D and L for that short-circuited stub or the open-circuited stub. One note that I'm going to make is that in this class, Z0 is going to be constant throughout our transmission line. In microwave engineering, you'll learn how to design stubs that might have a different characteristic impedance from the line. Two picture of an amplifier. It's actually a transistor that has been matched on both ends. There are two stub matching systems right here. So here's our transistor. You can see it right there. It's grounded at each of these points, which means it's a well-grounded transistor. And this is probably the input to that transistor. It comes through a capacitor, and then it has a stub here. This is the distance D, and here is the distance L. Now this is a microstrip, meaning that on the back side of this, if we looked at it from the back, there would be a copper plate on the bottom, and that's going to be grounded. And then there's going to be the sandwich of this white material that you see right there, and then there's going to be another copper trace on the top, which is this part. This particular stub is in parallel, and that's because it's connected with the same potential here as the transistor and the D point right there. And it is open-circuited because we don't see that anyone drilled a hole and short-circuited down to the copper at the bottom. So here's an example of a parallel stub that is open-circuited on the end. Now here's another one. This is the output, and it comes out. There's a stub right here of length L, and it's the distance D. There's a capacitor, blocking capacitor right there as well. So here is a picture of two stubs that are done in parallel, and what we want to define are D1 or D2 and L1 or L2. So in order to do that, we're going to need to be able to add series and lumped elements. So that's what the next video is going to be about.